Hello and welcome to the 11th Longevity Snapshot, where we will take a look at a Canadian study which uses Senolytics to treat lower back pain in mice. My name is Chris Linnell, and I am the founder and president of the Canadian Longevity Association, Canada's premier longevity nonprofit. If you'd like to find out more about what we do and how you can support us, then please take a look at the links below this video, where you'll also find a link to the study being reviewed here. In addition, if you enjoyed this video, then please give it a like and subscribe to our channel. Lower back pain is one of the most common chronic conditions of aging, affecting more than 80% of us at some point in our lives. It is a leading cause of disability and loss of quality of life. In the previous snapshot, Snapshot 10, we looked at how epigenetic reprogramming could reduce lower back pain, and you can find a link to that below this video as well. In this episode, we will see if removing senescent cells can also reduce lower back pain. As a reminder, senescent cells are cells which have become dysfunctional with age, releasing all sorts of detrimental molecules and factors, which cause problems throughout the body, and their removal can produce numerous benefits. Lower back pain is often caused by intervertebral disc degeneration, and this is accompanied by a buildup of senescent cells. Therefore, the authors wanted to see if removing those senescent cells could reverse that degeneration and, as a result, reduce lower back pain. Here is a study coming from the lab of Lisbeth Haglund of McGill University. But before we go into the details, let's take a look at a summary of the results. So the authors used two senolytics, O-vanillin, which is a main metabolite of curcumin, and RG7112, which is a synthetic molecule. And both of them successfully removed senescent cells from intervertebrate disc degeneration. O-vanillin and RG7112 affect different senescent pathways, so they work even better when combined. This resulted in reduced lower back pain in mice, a reduction in the release of SASP factors. So SASP stands for senescence-associated secretory phenotype, which is those detrimental molecules senescent cells release. There was also a lower degeneration score, and the vertebral bone quality improved. In addition, there was also a reduced expression of pain markers in the spinal cord. Altogether, this indicates that removing senescent cells was beneficial for lower back pain and could potentially provide a future treatment option for lower back pain in humans. Now let's take a look at the study in more detail, starting by briefly looking at Figure 1, which simply shows that the mouse model used in this study contained high numbers of senescent cells in their intervertebrate discs. The mouse model is called SPARK or SPARK null, which means that it doesn't contain the gene for SPARK. Now, SPARK is one of the most down-regulated genes in human intervertebrate disc degeneration. And mice which lack this gene get intervertebrate disc degeneration much sooner than normal mice. They get it after around 7 months, which is very early in a mouse's life. And you can see in B here, compared to wild type or normal mice, the SPARK mice had a higher grade of degeneration both in the upper and in the lower back, as you can see by the white bar being much higher than the gray bar here. They also had much higher levels of senescent cells in the intervertebrate disc, as you can see in B here, which was especially marked in the lower back. So NP stands for nucleus pulposus cells, which is the gelatine cushioning between the vertebrates, which act as a sort of shock absorber. And AF stands for annulus fibrosus, which is the collar around that shock absorber. In E here on the left, it simply shows that there was a high correlation between the number of senescent cells and the degeneration grade, as can be seen by this line going up by 45 degrees. There are also differences in gene regulation between the SPARK and normal mice, with a greater number of senescence-associated genes being upregulated in the SPARK mice. After confirming that there was an increased number of senescent cells in the SPARK mice, the authors moved on to seeing what the results would be by removing those senescent cells. So starting off with the study design in the top left here, at 7 months of age, when the SPARK mice were already having disc degeneration, they were given Senolytics weekly for 8 weeks, during which time they were assessed for pain and then sacrificed for analysis. Both male and female mice were used, and all the results are the combined results, as the authors found no difference between the males and females. There were 8 to 10 mice in each treatment group, and as you can see on the right here, there were a large number of treatment groups. Either O-vanillin on its own with either a high or a low dose, RG7112 on its own either with a high or a low dose, and I'll call RG7112 just RG from now on. Then they had 4 combination groups, either ovanillin and RG, both at high doses, ovanillin at a high dose and RG at a low dose, ovanillin at a low dose and RG at a high dose, and finally ovanillin and RG both at low doses. In all the graphs, they use the same color scheme to differentiate them. Gray indicates the wild type or normal mice. White indicates the spark untreated mice. Blue is the high dose ovanillin. Red is the high dose RG on its own. Green is the high dose vanillin and RG together. Yellow is the high dose of ovanillin and low dose RG. Purple is the low dose ovanillin and high dose RG. And brown is the low dose vanillin combined with low dose RG. The first assessment of pain in B and C here involved grip strength. So the mice had to hang on to a wire while their tails were pulled, which would obviously cause discomfort in the lower back, and with more pain they would let go sooner. And here you can see that over 8 weeks, the wild-type mice could hang on quite well, while the spark mice started off much worse, and the untreated spark mice, which is the black line, continued to get worse. Several of the other groups improved, as you can see by these rising lines. Looking at the area under the curve for that graph, you can see that in the first 4 weeks, there wasn't much difference between the untreated spark mice and the senolytic given mice. However, as in the graph on the left, between 4 and 8 weeks, there was a divergence, with the untreated spark mice performing worst, followed by the low combination dose of ovanillin and RG. Next best were the single high doses of ovanillin and RG, as well as the low dose ovanillin and high dose RG in the purple bar here. However, best performing was the high dose ovanillin, low dose RG, and the combined high dose group. And you can see a trend emerge both in this and in subsequent graphs, whereby the worst performing treatment group was the combined low dose ovanillin and RG, whereas the best performing group was the high dose ovanillin and RG, as can be seen by this green bar here. In the second pain assessment in D and E here, where they were suspended by their tails and it was seen how long it took before they would move around in discomfort. And once again, you had the wild type mice on the top here, and the untreated spark mice at the bottom, which continued to get worse. Once again, the best performing group at the end of 8 weeks was the combined high dose treatment group, which can also be seen in the area under the curve in E here, where after 4 weeks, there's not much differentiation between the untreated and the treated mice. However, after 8 weeks, there's a clear divergence, with once again the combined high treatment group showing the best results. Though it should be noted that after 8 weeks, it did not reach the same levels as the wild type mice. Though having said that, looking at the trend lines here, if the experiment had continued beyond 8 weeks, maybe they would have reached the same levels as the wild type mice. The final 2 pain assessments were cold sensitivity and mechanical sensitivity. For cold sensitivity in F, lower is better, as can be seen by the wild type mice at the bottom here. Once again, the untreated mice and the low dose combination group got worse over time, whereas the other treatment groups improved, with the best results seen in the high combination group and the high vanillin low RG group, which is once again shown in the bar graphs on the right, especially after 8 weeks, where, as you can see, the green and yellow bars are the lowest. In the mechanical sensitivity test in H and I, whereby a thin wire is run over the hind paw of the mice, higher is better, as can be seen by the wild type mice at the top here. And once again, the untreated and low dose combination group performed worst, while the high dose combination group performed best, as can also be seen by the bar graphs on the right here. And in case you're wondering, the stars at the top here represent statistical significance, so whether or not the results could just be down to chance or were likely because of the treatment. The greater the number of stars, the higher the statistical significance. Next, they looked at the release of those SASP factors, looking at 13 specific molecules. Now, I won't go into the details of all 13, however, a lot of them are inflammatory molecules, and lower levels are better. In this experiment, there are no wild-type mice as controls, so the results are only compared against the untreated spark mice. And as you should be able to see, treatment resulted in a decrease in the release of these 13 molecules. with the low-dose combination treatment group generally performing worst, as you can see by these brown bars, while the high-dose combination treatment group performed best, as you can see by the fact that the green bars are generally much lower than the other bars. The only exception being the release of the inflammatory marker IL-2, whereby the high-dose single O-vanillin group performed best. But it is clear that treatment resulted in a decrease in the release of these detrimental factors, especially with the combined high-dose group. Next, they checked that the senescent cells had in fact been removed. So P16 is a marker of senescent cells, and both in the nucleus pulposus and the annulus fibrosus, levels were markedly reduced compared to the untreated spark mice, with once again the combined high-dose group performing best and the low-dose combined group performing worst. This was further backed up by a reduction in the degeneration grade in E here, with the low-dose combination group showing no real reduction, however, the high-dose combination group showing the most reduction. And in C and D here, it shows simply a cross-section of the intervertebrate disc, and while the untreated spark mice clearly don't have any nucleus pulposus anymore, the high-treated single or combination groups maintain their intervertebrate disc, confirming the previous results visually. Next, they looked at what effects the treatment would have on the rest of the spinal cord. And once again, the spark mice had a lot more senescence compared to wild-type mice based on the senescent marker P16. However, after treatment, this marker was reduced, especially in the combined high-dose group. Next, they looked at immunoreactivity and specifically 3 molecules which are associated with pain. And once again, treatment resulted in a decrease in these 3 different molecules, with once again the combined high-dose treatment group performing best, especially for this one on the right. The low-dose combination group once again performed worst. Finally, the authors looked at the intervertebral disc and the quality of the bone, and in A on the left here, you can see the difference between a normal mouse and the spark mouse, and the normal mouse has a larger intervertebrate disc, as you can see with this red dashed line, whereas the spark mouse has a much smaller one, indicating less cushioning and support, and you can see by the disc volume in B here, wild-type mice have much larger volume than the spark mice. However, this volume increased upon treatment, and here we've only got 3 of the groups, so high-dose vanillin on its own, high-dose RG on its own, or the combined high-dose vanillin and RG. And just like in the previous figures, the combined high-dose group performed best, which saw a greater increase in volume, though this did not match the levels of the wild-type mice. If you sort of compare, looks like it goes to like 7.5 there, and only rises to 6 in the high-dose treatment group. Looking at cross-sections of the vertebrae, compared to normal mice, the spark mice had much greater gaps in their bones. You can sort of see these dark patches, while this was reduced in the treated mice, especially once again the combination treatment group. Before showing you the final figures below, which look at 2 specific areas of the bone, I should just quickly mention what they are. The first one is trabecular bone, and that is the inside of the bone, so cross section here is more spongy material. And the second one is the cortical bone, which is the hard outer shell of the bone. So starting with the trabecular bone, in G to L. First in G and J, this is showing the bone volume ratio. And first we have the wild type and spark mice. And you can see the spark mice have much lower volume of the spongy bone material. Whereas after treatment, this volume improved, especially for the combined high dose group. H and K shows the density. And once again, the spark mice have much lower density than the wild type mice. But this again gets improved after treatment. And I and L shows trabecular thickness, with the spark mice having lower thickness than the wild type mice. However, yet again, this got improved following treatment. Ending with the cortical bone in M to P, once again, the volume was lower in the spark mice compared to the wild type mice, which got improved in O here, as you can see by the higher bars. But this time, the higher RG single dose group performed best. Finally, in N and P here, we have MMI, which stands for moment of inertia, which is a proxy for the strength of the bone, or how it can sort of resist being bent. And once again, the spark mice had much lower strength, whereas after treatment, it improved, with once again the high dose single RG group performing best. So there we have it. Senolytic treatment clearly improved lower back pain in this mouse model and could provide a basis for treatment in humans. Importantly as well, both of these drugs appear to be safe, and I really hope that this gets tested in a human clinical trial. With this or the epigenetic reprogramming we saw in Snapshot 10, there could finally be a cure for lower back pain. Of course, what would be really interesting is to see what would happen if both of those treatments were combined. Hopefully some researchers out there will try just such an experiment. And that marks the end of another longevity snapshot. Please let me know what you thought of this paper in the comments below. If you enjoyed this video, please give it a like, share it with your friends, and subscribe to our channel. So until next time, goodbye.